In this video, we're going to talk about Mohr circle and stress elements. To begin with, what is stress? Stress is defined by F over A, the force over area. Then what is a stress element? For example, we have an object, a random object. We extract a point from this object, let's say point Q. Then we draw a cubic around Q, so as to say Q is the center of this cubic. Now on this cubic we have 6 planes. On each plane we have normal stress and shear stress. If we have a coordinate system like this, x is here, y is here, z is here, then this plane perpendicular to x, we call it x plane. This plane we call it y plane, and this plane we call it z plane. The normal stress on x plane is sigma x. The normal stress on y plane is sigma y. And for shear stress, tall xy stands for the shear stress on the x plane towards the y direction. And tall yz means the shear stress on plane y towards z direction. So for any stress element, we can use these quantities to represent the state. Normal stress, we have 3 of them, and shear stress, we have 6 of them. But for these two, and these two, they're equal. So actually we only need 6 of the quantities to represent the stress element's state. Now let's move on. For this shaft, we have this plane whose area is delta A, and this angle theta. The original coordinate system is in black, x and y. Now for this coordinate system, we can easily derive the force pointing here is sigma y times this area, which is delta A times sine theta. And here the force should be tau xy times the area, which is the same, delta A times sine theta. So what are we going to do is we want to rotate the coordinate system so that we can investigate this sigma x prime and also this tau x prime y prime. Now how do we do that? We can write 2 equations based on the current situation. The first equation is written on the direction of x prime. So we sub all the forces on x prime together, and then for the second equation we sub all the forces on y prime direction together. These 2 equations are actually looks quite complicated, but after some modification we can derive what is sigma x prime, sigma y prime, and tau x prime y prime, which is quite interesting because they are all functions of 2 theta. And then if we further plot it on a 2D plane, let's say the horizontal axis is x prime, the vertical axis is tau x prime y prime, then we can actually get a circle. How do we plot it? We just increase the theta value here. Increase every theta value. You can put the initial value of theta as 0, then increase it step by step. You can find as much points as possible and at the end the points will all locate on this circle. We call this circle Mohr circle. Now, on this Mohr circle, we have something to remember. These three equations are very important if we're solving problems related to stresses. This equation is simply the equation of the circle. The average point is the center of the circle, and this is the x, this is the so-called y, and this is the radius. So that is a typical circle equation. And of course, the average value, which is the center of the circle, can be calculated by sigma x, sigma y over 2. Here, the sigma x and sigma y can be any sigma. For example, we have a line here, and these 2 points should be representing this is sigma x, this is sigma y. You can use any of them value. You can choose a line here, okay, or here. They're all the same. And if you sub up and divide by 2, you will always get the average point. Then for the radius, actually this equation is derived by the upper equation. Now, after knowing this interesting point, how are we going to use this? For example, if we have another square drawn by the pencil, this is x direction, this is y direction. We want to know how do we rotate it, or on which direction does it reach sigma maximum and sigma minimum. Or we can also ask on which direction does it reach tau xy maximum or tau xy minimum. Actually, on the circle is quite clear that the point A is the maximum value, the point B is the maximum value, and for a certain cubic or a square in 2D cases, there must exist a point or an angle that corresponds to these maximum and minimum value. But our original position is like random. The original position x and y is random. It could be, as we drawn here, this could be the original location, and then a maximum location is here. So to reach the maximum location, we have to rotate it by a certain angle. And when we're rotating it on the Mohr circle, there's an important thing you should remember is that if we rotate it on the Mohr circle by 2 theta, on the actual graph, it only rotates by theta. For example, in red, this is the original direction, and we rotate it by theta. This is theta. So the stress state on the green direction should be the maximum value and minimum value. As you can see on the graph, we rotated by 2 theta, but in reality we're only rotated by theta. That actually makes sense because if you remember, in the original equation we derived, these are all 2 thetas. So when we plot it on the graph on the Mohr circle, the angles, the rotation angles, should also be 2 theta. Now for this question, for example, we know that there's exists a point or a direction which is x prime, y prime, that the normal stresses reaches its maximum. And this state can be only achieved by rotating the original square by theta p. How do we calculate the theta p? Actually, we can use what we derived earlier, this equation. Why? Because when the normal stress reaches its maximum, we can see it locates on the horizontal axis, which means the vertical axis, the value of torque x prime, y prime is 0. So if we want to know the information about this A point, we just let this equation to be 0. And we do some little modifications. We can move the cosine to the right, and then we divide the both sides by cosine 2 theta, so that we can easily get tangent 2 theta. So what is tangent 2 theta? It's actually like this. So on the graph, this should be sigma x, and this should be sigma y. Sorry, sigma x should actually be here. And this the shear stress should be tau xy. So given any original state, we can calculate how large is the angle that we should rotate to in order to get the maximum normal stresses. Now before the end, we have a question to practice. This is also a 2D case where the original position is like this. On the x direction, we have a 14 MPa stress, and on the y direction, we have a 20 MPa compression stress. So write it down. Remember, compression stress is minus. Then, of course, the first thing we should do is to plot the Mohr circle. To plot the Mohr circle, we should have the center and the radius. The center can be calculated by this equation. The summation divided by 2, which is minus 3, and the radius is 17. So this point is approximately minus 3, and we know the radius, so we can plot the Mohr circle. And what we want to know is the normal stress and the shear stress at this weld line. So of course, the thing we should do is to rotate the original coordinate system xy to the weld x prime, y prime, where the weld line is exactly parallel with this x prime axis. If we say this angle is theta, then pay attention. On the Mohr circle, we actually rotate it by 2 theta. And of course, from the graph, we can easily get sine theta value and cosine theta value. We have all the length of the sides. So yeah, it's pretty straightforward. So we get what is sine 2 theta, what is cosine 2 theta, and what we are doing is to locate the point Now, after we do the rotation, after we get the axis x prime and axis y prime, where is the point of sigma w? Sigma w is the normal stress on the weld line. Actually, the original 14 megapascal is here, and the original 20 megapascal is here. After rotation, the x value of this point should be the normal stress towards the x prime direction. And what we want is the normal stress towards the y prime direction, so we rotate it by another 90 degree on the real plane, which means we rotate by another 180 degree on the Mohr circle. So rotate, 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 then here. This is the point. So the x value of this point is the sigma w we wanted. So from the graph, it is the center minus r cosine 2 theta, which is minus 7.76. And the shear stress, as we said, the shear stress we can get from this point, which is minus r times sine 2 theta. Be careful, here there's a minus sign because on the Mohr circle, actually the y-axis stands for, it's always minus tau x prime y prime. So if you get this point, it seems like it's a positive value, but when you are converting to reality situation, you should do the minus.